Alright, let's dive straight into the fascinating world of EDA for VLSI. This is the engine room where digital dreams become silicon reality. So, where did it all start? Well, picture this. December 1947, Bell Labs. John Bardeen, William Shockley, and Walter Brattain are tinkering away, and boom, they invent the transistor. Suddenly, electronics aren't just bulky vacuum tubes anymore. It's like going from a horse-drawn carriage to a sports car. The graph here shows the incredible leap in computing power over time. See how the transistor era, marked in green, really kicked things off? It wasn't just about speed, it was about making things smaller, more reliable, and way more powerful. This single invention was the spark that ignited the entire semiconductor revolution. Fast forward a bit. We see the transistor taking center stage, but the real game changer was figuring out how to pack millions of them onto a tiny chip. That's where the journey towards VLSI begins. Look at the timeline here, especially focusing on the work of Martin Atalla and Da-Wan Kong at Bell Labs. Their patent in 1960 described the MOSFET, metal oxide semiconductor field effect transistor. This wasn't just another transistor. It was the foundation for the vast majority of chips we use today. It's the workhorse, the unsung hero behind your smartphone, your laptop, everything. Without the MOSFET, the explosion of modern electronics simply wouldn't have happened. Now, let's zoom in on that crucial patent, number 3, 102230, filed by Da-Wan Kong and Martin Atalla. This patent, granted in 1963, details the electric field-controlled semiconductor device. Essentially, it's the blueprint for the MOSFET. The diagram illustrates the basic structure: a semiconductor wafer, typically silicon, with a dielectric film, usually silicon dioxide, acting as an insulator. An electrode controls the flow of current through the semiconductor. This simple yet elegant concept allowed for the creation of transistors that were easier to manufacture and control than previous types. It was a pivotal moment, laying the groundwork for the integrated circuits we rely on today. These guys were visionaries. Interestingly, the story of the FET isn't entirely linear. Before Atalla and Kong's work, Julius Edgar Lilienfeld patented a similar device back in 1930. His patent, number 1745175, described a field effect tube using a solid conducting material. However, his invention didn't gain traction because high-purity semiconductor materials weren't available yet. Think of it like having a brilliant recipe, but no access to the right ingredients. His trap density was too high, meaning impurities interfered too much. So, while he gets credit for the early idea, the practical implementation waited for better materials and the work of Atalla and Kong. It's a reminder that even groundbreaking ideas can be ahead of their time. Okay, so we have the transistors, but how do we actually make them? It starts with something incredibly simple: sand. Yes, silicon dioxide, or sand, is the main ingredient. But it's not just any sand. It needs to be purified to an astonishing degree, 98% pure silicon. Then comes the magic of the Czochralski method. Imagine pulling a single perfect crystal from molten silicon, like a giant spaghetti strand, but perfectly ordered. This creates a silicon ingot, which is then sliced into thin wafers. These wafers are polished to mirror-like smoothness because even the tiniest imperfection can ruin a chip. It's a complex, multi-step process turning raw earth into the foundation of our digital world. Now, the moment of truth, the first integrated circuits. In 1958, Jack Kilby at Texas Instruments built the first integrated circuit. He managed to put a transistor, resistors, and capacitors all on one piece of semiconductor. Pretty cool, right? But there was a catch. The connections between these components weren't integrated. They were external wires, leading to low connectivity and limited performance. Fast forward to 1961, Robert Noyce at Fairchild Semiconductor came up with the first monolithic integrated circuit. Monolithic means all on one chip. Crucially, he figured out how to integrate the interconnects directly onto the silicon. This was a huge leap. It allowed for much higher density and performance, paving the way for the complex chips we have today. Kilby and Noyce are rightly considered co-founders of the integrated circuit era. Let's recap the key milestones quickly. We started with the transistor, the BJT, in '47. Then came the first transistor-based computer, TRADIC, in '54. Lilienfeld's MESFET patent was way back in '30. The silicon BJT followed in '54. And then, the game changer, the MOSFET, patented by Atala and Kong in '60. Each step built upon the last, pushing the boundaries of what was possible. The MOSFET, in particular, proved to be the most versatile and scalable, becoming the dominant technology for decades. It's a testament to incremental innovation, leading to exponential impact. So, how did these ICs evolve? From the early days of just a few transistors, we moved through generations of integration. Small-scale integration, SSI, think fewer than 100 transistors. Then medium-scale integration, MSI, large-scale integration, LSI, and finally, very large-scale integration, VLSI. Look at this table, it's mind-boggling. From under 100 transistors in the early '60s to over a billion by 2010. This isn't just a number. It represents the incredible miniaturization and complexity we've achieved. Today's smartphones contain billions of transistors, each performing a specific function. This relentless scaling, driven by Moore's law, has revolutionized everything from computers to cars to medical devices. With all these different ICs, how do we categorize them? There are several ways. First, based on the active devices used, bipolar junction transistors, BJTs versus field, effect transistors, FETs, which includes MOSFETs. Second, based on application, analog ICs handle continuous signals, like audio amplifiers, while digital ICs deal with discrete logic levels, like microprocessors. Third, based on technology, monolithic means everything on one chip, while hybrid involves combining multiple chips or components. And finally, based on the number of transistors, which we just saw, SSI, MSI, LSI, VLSI, ULSI, GSI. Understanding these categories helps us choose the right type of chip for a specific task. Now we get to the heart of the matter, physical design automation. What does it actually mean? Imagine you have a blueprint, a circuit description. Physical design is the process of turning that blueprint into a real, manufacturable layout on a silicon wafer. This involves creating geometric shapes representing transistors, wires, and other components across multiple layers. It's incredibly complex, dealing with millions of components and nanometer-scale dimensions. Doing this by hand? Impossible. That's why we need computer-aided design, CAD, tools. Physical design automation is the research and development behind these powerful tools, aiming to find the best way to arrange components and connect them efficiently to meet performance goals like speed and power consumption. Why is physical design automation so important? Because it's the backbone of the technologies we rely on daily. Think about VLSI itself, the ability to pack millions of transistors onto a chip. Embedded systems, like the microcontrollers in your washing machine or car engine, wouldn't exist without efficient ways to design and manufacture these complex chips. The Internet of Things, connecting billions of devices, depends on low-cost, high-performance chips designed using automation. And the Industrial Internet of Things, optimizing factories and supply chains, also relies heavily on sophisticated VLSI design. Essentially, VLSI is the foundation, and physical design automation is the sophisticated machinery that builds upon it, enabling the digital age we live in. When we talk about designing chips, we often encounter different types of ICs. Let's compare three main ones: ASICs, FPGAs, and SoCs. ASICs are application-specific integrated circuits, custom-made for one specific job. Think of them as bespoke suits, highly optimized but expensive and slow to design. FPGAs are field-programmable gate arrays, like configurable Lego bricks. You can reprogram them for different tasks, great for prototyping or low-volume production. SoCs are system-on-chips, packing a whole system onto one chip, CPU, memory, peripherals, etc. They offer a balance of performance and flexibility, often used in complex devices like smartphones. Each has its own sweet spot in terms of cost, performance, and time to market. So, how do we actually go from an idea to a finished chip? It follows a structured process, the VLSI design cycle. It starts with defining exactly what the chip needs to do, the system specification. Then, we figure out the overall architecture, the high-level design. Next, we break down the functions and define the logic. After that, we translate the logic into actual circuit elements. Finally, the physical design phase takes over, laying out the chip on silicon, followed by fabrication and packaging. It's a journey from abstract concept to tangible product, involving many steps and checks along the way. Let's drill down into the first few stages. System specification is where the rubber meets the road. Designers talk to customers, engineers, market folks to figure out exactly what this chip needs to do. What's the target speed? How much power can it consume? What features are essential? It's like writing the requirements document for a software project, but for hardware. This stage is crucial because it sets the direction for everything else. It's a balancing act between what the market wants, what the technology allows, and what makes economic sense. Get the specs wrong, and the whole project could be off track. Next up is architectural design. Here, we decide the high-level structure of the chip. For a processor, this means choosing between RISC and CISC architectures, deciding how many arithmetic logic units ALUs or floating point units FPUs we need, how the pipeline will work, and how big the caches should be. It's like designing the blueprint for a building, deciding the number of rooms, floors, and elevators. The outcome is often a microarchitectural specification, MAS. This MAS is a detailed description that allows architects to predict the chip's performance, power consumption, and size before writing a single line of code or drawing a single transistor. It's a critical step for ensuring the design meets the initial specifications. Functional design, sometimes called behavioral design, is where we break down the architecture into its main functional units. Think of the CPU core, the memory controller, the I/O interface. We identify these blocks and figure out how they interact. We estimate the area, power, and timing for each block. Importantly, we focus on the behavior, the what, not the how. For example, we might specify that we need a multiplier unit, but not yet decide if it's a fast, complex one or a simpler, slower one. This allows for flexibility and optimization later on. It's like defining the major departments in a company and their responsibilities without detailing the office layout yet. The key takeaway here is abstraction. Functional design specifies the inputs, outputs, and timing relationships between units without getting into the internal wiring or transistor details. The result is often a timing diagram showing when signals should be active. This high-level view is fantastic for simulation and debugging early on. If the system doesn't work as expected, you can fix the functional design relatively quickly. It's mostly a manual process, relying on the designer's expertise to understand the system's behavior. It's like writing pseudocode for a program, focusing on the algorithm rather than the specific programming language syntax. Now we move from behavior to implementation. Logic design is where we translate the functional requirements into the actual control flow, data paths, and operations. We define the word widths, how registers are allocated, and the specific arithmetic and logic operations needed. This detailed description is captured in the register transfer level, or RTL. Think of RTL as the assembly language for hardware. It describes how data moves between registers and how operations are performed. It's a crucial step because it's the input for the synthesis tools that will eventually create the physical layout. How do we express this RTL description? Using hardware description languages, or HDLs, like Verilog or VHDL. These languages allow us to describe the hardware's behavior and structure. The RTL description includes Boolean expressions and timing information. A key part of logic design is minimizing these Boolean expressions to get the smallest possible logic circuit that still performs the required function. This minimized logic is then simulated and tested extensively to ensure it's correct. Sometimes, special tools called high-level synthesis can automatically generate RTL code from a higher-level behavioral description, speeding up the process. Circuit design is where we get down to the nitty-gritty of transistors and gates. Based on the logic design, we convert the Boolean expressions into a detailed circuit diagram. This involves selecting specific transistors, arranging them into gates like NAND, NOR, AND, OR, and connecting them together. We have to consider the speed and power characteristics of the chosen components. Circuit simulation is vital here to verify that the circuit works correctly and meets the timing requirements. This detailed circuit diagram is often called a netlist, which lists all the components and their connections. Tools called schematic capture tools help designers create these diagrams, though often, synthesis tools can automatically generate the netlist from the RTL description. Finally, we arrive at physical design. This is where the abstract circuit netlist becomes a concrete geometric layout. We take the transistors, gates, and macros, and represent them as shapes on different layers of the silicon wafer. Connections between components become lines or vias connecting these layers. Think of it as translating the electrical blueprint into a physical construction plan. This layout must adhere to strict design rules dictated by the fabrication process. It's a complex puzzle, fitting millions of pieces together perfectly. Creating this layout isn't arbitrary. It's governed by design rules, which are essentially the rules of the game for the foundry. These rules dictate minimum distances between wires, maximum widths, allowed layer combinations, and so on. They ensure the chip can be manufactured reliably. Because physical design is so complex, it's broken down into sub-steps like partitioning, placement, routing, and compaction. Throughout this process, verification checks are performed. While some aspects can be automated using layout synthesis tools, especially for standard cells, many parts still require manual intervention or sophisticated algorithms. Who does the physical design? For high-performance chips like microprocessors, it's often a mix of manual and automated work. Skilled engineers manually place critical blocks and optimize tricky areas, while CAD tools handle the repetitive tasks. For lower performance designs, or when time to market is critical, layout synthesis tools can automate much of the process, although they might sacrifice some area and performance compared to a fully optimized manual layout. As designs get bigger and more complex, the challenge of manual optimization grows, making automation increasingly important, even for high-performance chips. Look at this Pico-SoC layout. It shows how different functional blocks are arranged and interconnected. Once the physical design is complete and verified, it's time for fabrication. This is where the magic happens in the cleanroom facilities of semiconductor fabs. The layout data, often sent on a tape, triggers the creation of photolithographic masks. These masks are like stencils, defining the patterns for each layer of the chip. Silicon wafers are prepared, polished to perfection, and then undergo a series of complex steps involving deposition, etching, doping, and metallization, all guided by the masks. It's a multi-stage process, potentially using dozens of masks to build up the intricate layers of the circuit. Before mass production, a prototype chip is made and rigorously tested. Let's talk a bit more about fabrication. The layout data is converted into masks, one for each layer of the chip. These masks define the patterns to be transferred onto the silicon wafer. Silicon ingots are grown, sliced into wafers, and polished to an atomic level of smoothness. The fabrication process involves depositing thin films of materials like polysilicon, oxides, and metals, and then selectively removing them using etching processes guided by the masks. Multiple layers are built up, creating the transistors and interconnects. Because of the complexity, the entire process can take weeks or months. And yes, before you start making millions of chips, you make a few prototypes to test everything works. Look at the evolution of wafer sizes. From tiny 2-inch wafers in the late 60s to the massive 12-inch wafers used today, and even 18-inch ones being developed. Why? Bigger wafers mean more chips per wafer, which significantly reduces the cost per chip. It's a constant push for larger diameters. The table shows the progression, and the image gives you a sense of the scale. Each wafer is a canvas, and the challenge is to paint the most complex and functional circuit possible within its confines. It's a testament to the scale of modern manufacturing. The final stages are packaging, testing, and debugging. After fabrication, the wafer is cut into individual chips, a process called dicing. Each chip is then packaged, often in formats like DIP, PGA, BGA, or QFP, which provide pins or balls for connection to the outside world. Packaging protects the delicate chip and provides electrical connections. Then comes the crucial testing phase. Every chip is tested to ensure it meets the design specifications and functions correctly. Defective chips are discarded. Only the good ones proceed. For some applications, like multi-chip modules, the chips are used bare, without packaging. This ensures the final product is reliable and performs as intended. Things are changing rapidly in the VLSI world. One big trend is increasing interconnect delay. While transistors are getting faster, the wires connecting them aren't scaling down as fast. In fact, the delay caused by these interconnects can dominate the overall path delay. Look at the graph. Decades ago, gate delay was king. Now, interconnect delay is a huge factor. One solution? Repeater insertion, adding small amplifiers along long wires to boost the signal and reduce delay. This requires careful planning up front. It's a fundamental shift in how we think about chip performance. Another consequence is increasing interconnect area. Because the interconnects are becoming slower and more critical, we need more space for them. Estimates show that a significant portion of a modern microprocessor die, maybe 40% or more, is dedicated to wiring. Early ICs had just one metal layer, but now we have 4, 5, even 6 layers. Adding more layers helps reduce the total area needed for interconnects, but it's not a perfect solution. Each via, the vertical connection between layers, takes up space too. So, the challenge is to manage this growing interconnect footprint efficiently. To cope with the interconnect demands, we've seen an increasing number of metal layers. Modern chips often use 3, 4, or even 5 layers of metal for wiring. This creates a three-dimensional structure. Look at the SEM image. It shows the intricate copper wiring. The diagram illustrates the different layers, from local connections near the transistors to global buses spanning the chip. Managing these layers, routing signals through them, and ensuring they don't interfere with each other is a major challenge in physical design. It's like building a multi-story highway system on a tiny piece of land. All these trends, interconnect delay, area, and layers, lead to increasing planning requirements. Where you put things on the chip matters hugely. Physical design considerations can't wait until the end. They need to be baked in early. Functional design now often includes chip planning. This involves block planning, figuring out the shapes and locations of major functional blocks, and signal planning, deciding the 3D paths for critical signals and buses. We need to estimate timing early on to validate the plan and set constraints for later stages. It's a more holistic approach, requiring foresight and planning from the start. How can we speed up the design process? Synthesis. Instead of manually designing every transistor, can we automate it? Logic synthesis is a mature technology that takes a high-level description, like Verilog or VHDL, and automatically generates the corresponding circuit diagram, the netlist. It's widely used for smaller blocks within a chip. However, it struggles with large, regular structures like RAMs or entire microprocessors due to speed and area inefficiencies. The example here shows a simple Verilog module for an adder. Logic synthesis tools would take this description and generate the gate-level implementation. Taking automation further, we have high-level synthesis, or HLS. This aims to go from an even higher level description, capturing just the behavior, perhaps in C or C++, directly to a layout or RTL description. It's a much more ambitious goal. The tools range from general-purpose systems to specialized ones for specific architectures like DSPs, sometimes called silicon compilers. Module generators are even more restricted, handling smaller problems. While HLS is still largely research and not widely used in mainstream chip development yet, it holds huge promise for drastically reducing design time, especially for complex systems. The diagram shows the concept, inputting an algorithm, and getting out hardware description. Because of all these new challenges and trends, the traditional VLSI design cycle is evolving. Look at this updated flowchart. Notice the emphasis on early integration of physical design considerations. Verification is now woven throughout the process, not just at the end. Steps like floor planning, placement, and routing are happening earlier, driven by timing and power constraints. This iterative approach, checking and refining as we go, is becoming essential to handle the complexity and ensure the final chip meets its demanding targets. Let's focus specifically on the physical design cycle. The input is the circuit netlist, and the output is the final layout. It's a multi-stage process. First, partitioning breaks the large design into manageable blocks. Then, floor planning and placement determines the overall layout and positions the blocks. Next, routing connects the blocks according to the netlist. Compaction shrinks the layout to save area. Finally, extraction and verification checks the layout against design rules and verifies its functionality. Each step is critical and builds upon the previous one. Here's a more detailed view of the physical design flow. It starts with the netlist, the detailed circuit description. Then comes the crucial step of physical design, which includes partitioning, floor planning, placement, and routing. Often, clock tree synthesis is done during routing to distribute the clock signal efficiently. After routing, timing closure is performed to ensure the chip meets its speed requirements. Finally, extraction and verification checks the layout against the original design. Only then can we move to fabrication and packaging. It's a complex, iterative process, requiring sophisticated tools. Partitioning is the first step in managing complexity. A modern chip might have millions of transistors. Trying to lay out the entire thing at once is computationally impossible. So, we divide the chip into smaller, manageable blocks. The partitioning process considers factors like the size of each block, the number of blocks, and how many connections exist between them. The goal is to create a hierarchy of blocks, maybe starting with 5 to 25 top-level blocks, which are then further subdivided. The diagrams show examples of cutting a circuit into different blocks. The second diagram shows a 48-bit input split into 3 blocks of roughly equal size. Floor planning is about deciding the overall shape and arrangement of the chip and its major blocks. We estimate the area needed for each block and consider the interconnect area within the block. The shape of the block, its aspect ratio, can be adjusted. Floor planning is super critical because it sets the stage for everything else. However, it's computationally hard. So often, experienced engineers do it manually, visualizing the flow of information. The objectives are clear: minimize area, minimize timing, reduce wire lengths, make routing easier, and reduce voltage drop. The diagram shows the typical layout of a chip, with I/O pads, power rings, and the core area containing the main logic and macros. Placement is the next step, putting the blocks onto the chip. The goal is to find the best arrangement that minimizes the total area while allowing all the required connections to be made. It's typically done in two phases. First, an initial placement is created, often randomly. Then, the algorithm iteratively improves this placement, moving blocks around to reduce congestion, shorten wire lengths, and improve timing. Sometimes, the initial placement might be unroutable, meaning there's no way to connect everything. In that case, we might need to go back and replace the blocks. Estimating the routing space needed during placement helps avoid this problem. In the context of standard cell design, placement refers to placing the pre-designed standard cells onto the chip. The CAD tool uses algorithms to determine the optimal location for each cell. It's not just about placing them, it's also about optimizing the design for area, timing, and power, and ensuring the design is routable. Placement is driven by various criteria, such as minimizing area, meeting timing targets, or reducing power consumption. The diagram shows the typical layout of a chip using standard cells, with the core area filled with these cells, surrounded by macros and I/O ports. Routing is the process of drawing the wires to connect all the pins of the blocks and cells. The space between the blocks is divided into channels and switch boxes, which are the areas where routing happens. The router's job is to find paths for all the wires, ideally using the shortest possible length and staying within the allocated routing space. This is usually done in two phases: global routing and detailed routing. Global routing finds the general path for each wire, specifying which channels and switch boxes it should use. Detailed routing then draws the exact geometric path for each wire, considering layer assignments and avoiding overlaps. Within the routing process, we have specific techniques. Switchbox routing deals with routing signals through these programmable switchboxes, which act like crossroads connecting different layers. The goal is to find efficient paths through the switchboxes. Channel routing focuses on routing wires within the narrow channels between rows of cells. It involves placing wires vertically within these channels to connect pins on adjacent cells. Both techniques aim to minimize wire length and congestion while ensuring all connections are made. The diagram shows the flow from global routing to detailed routing, highlighting the transition from loose paths to precise geometry. Compaction is the process of shrinking the entire layout to save area. By compressing the layout in all directions, we reduce the total chip size. This has several benefits. Shorter wire lengths mean less signal delay. A smaller chip means more chips can be produced from a single wafer, reducing manufacturing cost. However, compaction is computationally expensive, so it's usually reserved for high-volume applications where the cost savings justify the effort. Crucially, compaction must not violate any design rules. The diagram shows the concept of shrinking the layout while maintaining the integrity of the design. Before we can send the layout to the fab, we need to verify it thoroughly. This is extraction and verification. First, design rule checking, DRC, verifies that the layout meets all the geometric rules imposed by the fabrication process. For example, it checks if wires are close enough together. Next, circuit extraction reads the layout and generates a netlist, essentially reverse engineering the circuit. Layout versus schematics, LVS, compares this extracted netlist to the original circuit design to check for correctness. Performance verification extracts parasitic capacitances and resistances to accurately simulate the timing. Finally, reliability verification checks for potential failure mechanisms like electromigration. The diagram shows the detailed structure of a transistor, highlighting the geometric parameters checked by DRC. Let's revisit those new trends in the physical design cycle. Remember the increasing importance of interconnect delay? This means we need to think about timing much earlier. One key strategy is chip-level signal planning. We need to plan the routing of major signals and buses from the very beginning of the design process. This means minimizing the distance these signals travel and routing them on the top metal layers, which have the lowest resistance and capacitance. It's about strategically placing and connecting the critical pathways of the chip early on. Another technique is over-the-cell, or OTC, routing. Traditionally, routing happened in the channels between cells and the switch boxes. OTC allows routing to go over the top of the cells themselves. This can be very effective for reducing area and improving performance, especially for long, critical signals. It essentially makes routing a three-dimensional problem. Another consequence of OTC is the arbitrary terminal model, or ATM. Instead of bringing pins to the edges of the block for connections, pins are brought to the top surface, allowing for more flexible routing. The diagram shows the iterative nature of the design process, with feedback loops for timing and size checks. Here's a summary of the VLSI design cycle, emphasizing the integration of physical design considerations early on. From the initial system specification, through architectural and functional design, logic design and circuit design, physical design steps like partitioning, floor planning, placement, and routing are performed iteratively. Clock tree synthesis and signal routing are crucial for timing closure. Throughout this process, verification and validation are essential to ensure the design meets its requirements. This modern approach acknowledges the complexity of today's designs and the need for early planning and optimization. Now, let's talk about different design styles. Broadly, we can classify them as full custom or semi-custom. Full custom design gives you maximum control. You can place blocks anywhere on the chip. Semi-custom uses pre-designed components, like standard cells or gate arrays, which have fixed locations. The choice depends on the project type, cost, and time to market. Full custom is great for high-performance, mass-produced chips, but takes a long time. Semi-custom offers a faster route to market, suitable for ASICs. Sometimes, programmable devices like FPGAs are considered separately. The diagrams show the classification hierarchies. Full custom design is the original, hands-on approach. You design everything from scratch, from the transistor level up to the full chip. It requires immense effort and expertise to achieve high quality and performance. The cost is high, but it can be amortized over huge volumes. Think of the early Intel 4004 processor, the first commercial microprocessor. It was designed using full custom techniques. Today, it's very difficult to practice full custom design for entire chips due to the sheer complexity and transistor counts. It's mostly confined to specific parts of larger projects or highly specialized applications. Full custom design is typically hierarchical. The chip is organized into clusters, which contain units, which are composed of functional blocks. The beauty of full custom is that you can tailor the size and shape of these blocks precisely. You can place them anywhere on the chip surface without restrictions. This lack of constraints allows for highly compact and optimized designs, achieving the best possible performance and area. Figure 1.5 shows a typical full custom structure, with various functional blocks like data path, I/O, memory, and logic interconnected. The internal routing within each block is usually hidden for clarity. Standard cell design is a popular semi-custom approach. It uses a library of pre-designed, reusable cells, typically logic gates like NAND, NOR, AND, OR, and flip-flops. These cells are designed once and characterized for performance. The designer partitions the circuit into blocks that match the available cells. Cells are placed in rows, and the space between rows is used for routing. The diagram shows a cell library with different types of cells and a feed-through cell used for routing between non-adjacent rows. This approach simplifies the design process compared to full custom. Standard cell design is inherently non-hierarchical, so hierarchical circuits need transformation. It's well suited for moderate-sized circuits and medium-volume production. Physical design is simpler than full custom, especially with modern CAD tools. Logic synthesis tools often target standard cell libraries. While faster to develop than full custom, creating the cell library itself is a massive undertaking, requiring skilled designers and significant resources. Each cell needs to be simulated and characterized. Standard cell designs typically take more area than fully optimized full custom designs, but the gap is narrowing with better routing tools and more metal layers. Gate array is another semi-custom style. It's simpler than standard cell. The chip is prefabricated with a regular array of identical transistors, or gates. The designer's job is to connect these pre-made gates using the routing layers added later. The partitioning and placement phase becomes a block-to-cell assignment problem. The number of blocks must be less than or equal to the number of cells. Once the connections are defined, the routing layers are fabricated. The completed wafer is called a customized wafer. The main goal of routing here is simply to complete the connections, not necessarily to minimize area. The advantage of gate arrays is speed and cost. Since the base structure is prefabricated, the customization steps are faster and cheaper than full custom or even standard cell. Like standard cell, gate array is also non-hierarchical. The diagram shows a conceptual uncommitted gate array with rows of potential transistors. The circuit diagram shows how a simple logic function, like an XOR gate, can be implemented using these prefabricated gates and the routing network. It's a trade-off between flexibility and performance. Finally, we have FPGAs, field programmable gate arrays. These are highly flexible, programmable devices. They consist of a grid of configurable logic blocks, CLBs, and a programmable interconnect network. Users can program the interconnect to implement different logic functions. FPGA cells are more complex than standard cells. They offer rapid prototyping and reconfiguration, making them ideal for low-volume production or applications where flexibility is key. The diagrams show the internal structure of a CLB, typically containing a lookup table, LUT, and a flip-flop, and the overall FPGA architecture with programmable interconnects. Let's summarize the comparison. Table 1.1 shows differences in cell size, type, placement, and interconnect. Full custom is flexible but costly. Standard cell offers a good balance. Gate array is simpler and cheaper, but less flexible. FPGA is highly flexible, but typically larger and lower performance. Table 1.2 compares area, performance, and fabrication layers. Full custom and standard cell use all layers for maximum performance and compactness. Gate array and FPGA use fewer layers for customization, impacting performance and area. Choosing the right style depends on the specific application needs. And that brings us to the end of this introduction. We've covered the basics of VLSI design, the evolution of ICs, the physical design process, and the different design styles. Hopefully, this gives you a solid foundation to explore the fascinating world of electronic design automation for very large-scale integration.